So, welcome back. Today we will switch tracks a little bit. We've been talking about semiconductor light sources during the past few lectures, and what we will talk about today is semiconductor light detectors. And once again, we are going to rely on the familiar PN junctions, right. So, as we saw before, when we consider PN junction diode, so what we have is the excess holes are going over to the N side from the P side, and that is leaving behind some fixed charges, negative charges on this side and positive charges on this side, right. And the corresponding energy level diagram will be such that on this side you have the conduction band here, on this side you have the valence band here. So, you have the conduction band from this side going like this. Right. Now, what we are talking about is a light detector. So, what we are saying is if you have h nu such that h nu is greater than Eg, the band gap energy, then what you will have is light will be absorbed by this material and it absorption is such that it takes an electron from the valence band to the conduction band, leaving behind a hole in the valence band. So, you are essentially generating an electron hole pair, and of course, the electron is going to go this way, and similarly the holes are going to go this way, and that generates the photocurrent in the external circuit. Now, as we saw before, the presence of these fixed charges at the junction, that creates an electric field, right. So, you have, when you are looking at the magnitude of the electric field at the junction, you have something like this, right. And that electric field also is represented over here as E times V naught, right. That's basically a barrier that's built in there, which prevents just diffusion of electron hole pairs without any external illumination, right. Without any external illumination, it is all at equilibrium. So, there is no transfer of charges across that barrier, right. But in the presence of light, when light actually falls on this photodiode, it generates electron hole pairs, and then those electron hole pairs, the inbuilt electric field actually ends up pushing those electrons to the right side and holes to the left side. Okay. Now, interesting things happen once again when you have a bias, when you give an external bias to this. So, but this time, unlike the case of light sources, we are giving a reverse bias over here, and when you give a reverse bias, what happens is, let us say reverse bias VB, we said this potential is going to be modified, that barrier is going to be modified such that in this case now, because it is reverse bias, you have enhancement of the barrier. The forward bias case, we were saying that the barrier height gets reduced. but here we are saying it results in an enhancement of the barrier. So, the corresponding electric field gets enhanced in the presence of this external bias. Okay. So, one obvious effect of that is, so you have a much larger barrier height. So, the electrons actually flow faster across the junction, electrons flowing towards the right side and holes flowing towards the left side. The mobility is increased because of this external field. And it's such that when we talk about mobility, we talk about the velocity of these charges. When we look at that as a function of the electric field, okay, what happens is normally without any electric field, you have the diffusion process happening. So, these charges just diffuse, and of course, they cannot diffuse beyond that built-in potential. But within the influence of the electric field, it actually increases and then it saturates. Okay. So, this is actually what is called drift. So, the drift mechanism happens under the influence of the electric field. So, larger the electric field, larger we are tracking the velocity of these charge movement, charge particles movement, and we are basically saying that under the influence of electric field, the velocity increases and it achieves a saturation velocity which is in the order of 10 power 5 meters per second. This diffusion velocity is in the order of 10 power 3 meters per second. Okay. So, so clearly we can say that these charges get swept out faster as due to this drift process. Now, what is the effect of that on this response of this photodiode? Effect is in terms, we can look at that effect in terms of time, the temporal response. So, let us say this is actually the photocurrent. So, IP let us say is the photocurrent generated because of light falling on this photodiode. If you have an incident pulse that is like a square pulse, incident optical pulse that is square in shape, how is the photodiode going to respond to this? Well, what you are going to see is typically this is going to respond fast and then it is going to slow down, right. And similarly, when you turn off the light input, there is going to be a fast decay and then there is going to be a very slow decay. Okay. So, how do you explain this? Now, clearly we say that any charge under the influence of the electric field is going to have a higher velocity. So, those are the charges that you are going to see come out of that is going to contribute to the external photocurrent, right. So, in this region we have drift and then this slow response actually corresponds to diffusion, right. So, you can say that diffusion is going to be a process that limits the response of your photodiode, which is based on just a PN junction diode. Do you understand this? Right. So, it is not a question of whether you can get a photocurrent or not, right. That we already know let's see, the other day we were talking about the IV characteristics of your photodiode, right. So, let's say this is I and this is V, and we were talking about how it behaves in the forward bias. It's going to have an exponential dependence on the forward bias voltage, and in the reverse bias it's going to come out like this. So, there is going to be a certain current which we were previously calling as IS, right. We were calling as IS. So, there is going to be a certain photocurrent that's going across at reverse bias. Now, when you point here is we are trying to use it as a photodiode. So, what happens when you increase the amount of light that falls on this photodiode? You essentially have a shifting of this curve. So, as you increase, this level is going to increase, right, and so according to so what we are saying is, as light intensity increases, as the light intensity increases, initially you have when there is no light falling on the photodiode, there is no photocurrent, but as you increase this light intensity, the corresponding current increases. And this is actually a very important point to note. A lot of people tend to get confused about the role of the reverse bias. Okay. They tend to think that as you go to higher reverse bias, you get more current, photocurrent out of the photodiode. Okay. That is a common misconception. You do not need any bias just to generate the photocurrent itself, right. Photocurrent is generated just by the simple principle that if your light energy is greater than the band gap energy, it is going to generate electron hole pairs, and those electron hole pairs are going to diffuse across and find their way to the external circuit. So, even without bias, as you increase your light intensity, you are still going to get a photocurrent. So, then what is the role of that external bias? If you do the reverse bias, what does it improve? It improves the velocity with which these carriers move. So, it improves the response time basically, right. So, without any external bias, the response time would have been all due to diffusion, except for those carriers that are generated in the depletion region itself, right. Everything else would have been under the influence of diffusion, so it would have been a very slow response, right. So, you are increasing your external bias primarily to improve the response time. But nevertheless, coming back to this picture here, if you want to have a high speed response, you need to essentially encourage drift and you want to discourage diffusion, right. So, how do you do that? Now, it turns out there is a very neat way of accomplishing this. So, you just go for what is called a PIN structure. So, what do you have in a PIN structure? You have your PN regions and then you have I region. What does I correspond to? Intrinsic semiconductor. So, it does not have the electron and hole concentration are the same essentially in an intrinsic semiconductor, and the Fermi energy is right in the middle of that band gap, right. So, in this case, when you look at the charges that are present, the charge density is going to be such that you are going to have negative fixed charges over here, positive charges over here, okay. And when you, so in terms of charge density, if you were to look at what's happening, this is actually, so this is charge density, right, and you have positive charge density over here. But key is what do you see when you are looking at that magnitude of the electric field? Okay, when you look at the magnitude, the electric field you can find by applying Gauss law across this entire structure. And if you look at the magnitude of the electric field, that's going to be like, it's going to increase like this, and then in the intrinsic region there is no potential drop, there is no work done, right. So you would essentially maintain that electric field, and then comes down when it goes through this N region, right. So what you have managed to do is distribute your, if you do an external bias now, distribute that bias across that entire I region, right. And if you make your P and N regions relatively much smaller, then you can say that across the entire structure you have an electric field. If you have an electric field, what happens? You are encouraging the drift process. So, there is very negligible diffusion that is happening. So, intrinsically this sort of a structure is going to give you a very fast response time, okay. So, that is one of the major advantages of going to a PIN photodiode. And thing is that the I region can be extended to whatever width you want. Why is that important? Because the typical way of illuminating this is going to be, you're going to have your electrodes defined like this, and you're going to illuminate from here, right. Because if you think about the structure, it's epitaxially grown, so it's grown from N, I, P and so on, right. So it's just easy to illuminate from here, and if you do that illumination, that light is going to get absorbed as it propagates through this material. And how is that absorption going to happen? What is the profile of that absorption, or the power as it goes through? That is going to go down exponentially. So, you are going to basically have an exponential profile for the light that's propagating through that structure. And so the width of that I region, let's call that W, right. So that the width of the I region can be extended so that you can absorb all the power that's incident on this structure, right. So it gives you a sort of a free sort of design parameter. So by changing the value of I, changing the value of W, or rather increasing the value of W, you can absorb all the light that's falling on the photodiode. So the electron and holes are generated all across, right, and if the electron hole pairs are generated in the depletion region, then they are under the influence of the electric field, so they get pushed out faster. But if the electron hole pairs are generated anywhere else, they are under the process of diffusion, So when we look at this graph closely, there is a slight difference between the current that you have at 0 bias and the current that you have at some finite value of bias. Basically, that will account for the electrons that you would lose in this process, or holes that you would lose on the other side as well. They are not actually seeing the external circuit, so they don't contribute to that photocurrent, right. So there will be a slightly lower current generated at 0 bias compared to some higher value of the bias voltage. Yes, so the question is, can we just review this IP versus time? So what we are saying is that illumination is given by this dotted line over here, that corresponds to the power as a function of time, right. So you would want ideal photodiode to have the photocurrent follow that same dotted line. But because of the fact that only the carriers generated in the depletion region are going to be under the influence of this drift process, the high velocity thing. Those are the ones that will come out of the photodiode first. So those will contribute to the initial photocurrent, and then you have the slower sort of charges coming out of this photodiode, right. So the ones that are going through the diffusion, so then they would have a slower time constant. They will come later, essentially, right. And what we have fixed with the PIN structure is that now you can get a response something like this. So this will be the response of a PIN structure, right. So that's what we are talking about. And then of course what we are also saying is that by changing the width of I, you can actually show how the power is getting absorbed across that structure. So maybe we can, so just to emphasize this point, all this region across this entire region you have the drift process dominating, so that gives a better response from the photodiode. So let's now track the characteristics of the photodiode. Let's start with responsivity of the photodiode, right. So responsivity, which is denoted by R, is essentially given by the photocurrent generated, let us say IP, for a certain level of power that is incident on the photodiode. So this is in units of amperes per watt. So let us now try to find an expression for IP. So what exactly is happening when light falls on this photodiode? Now light falls on this photodiode at a certain rate, okay. That rate is given by that flux is given by power over photon energy, right. So P in over h mu is the rate at which the photons are incident on this, and when they are incident on that material is a high index material, right. So you are coming from air into a high index material. So you are going to have certain losses due to reflection at the surface, right. Let us say RF is the reflectivity at the facet. So RF corresponds to the reflectivity at this facet over here, Okay. So, 1 minus RF is what is coming in, and those photons are going to generate electron hole pairs, and that is actually a sort of a quantum phenomena. So, it is not like every photon generates an electron hole pair. There is a certain efficiency with which that conversion happens. That efficiency we will denote as zeta, right. So, that is actually the photon to electron hole pair conversion efficiency. To give you an idea, zeta will be fairly high, it's in the order of 0.9 for in gas, which is a direct band gap semiconductor, whereas it's around 0.7 for silicon, which is a indirect band gap semiconductor, right. And then of course, you are generating charges, so you can represent that electronic charge as E, and then what is the amount of light that is absorbed within this medium, that is going to be given by a factor 1 minus e power minus alpha multiplied by W, right. If W is the width of your structure, right, e power minus alpha times W is the power that is a fraction of power that you have at the end of the device. So, the power absorbed will be 1 minus e power minus alpha W. Okay. So, based on this expression, you can write the responsivity as some factor eta, right, multiplied by E over h nu, right, where E is the electronic charge, h nu corresponds to the photon energy, and eta is essentially a product of these three, those three terms determine value of eta, and that is going to be in amps per watt. And of course, you have H is a constant, E is a constant. So, if you work that out, what you will find is this is going to be given by some factor of 1.24. So, nu you can write it as C over lambda, right. So, H, C and E are all constants. So, you are going to have 1.24 or rather eta lambda divided by a factor of 1.24, where lambda is expressed in microns. So, that is actually a relatively easier thing to compute. So, eta now your RF can be reduced. How do you reduce RF? The reflectivity at the facet? You could do an anti-reflection coating there, right. So, that can reduce RF. In zeta you can, well, you are stuck with whatever material that you are given, right. So, if it is a direct band gap, then that is 0.9 or it could be even 0.95. The material purity is very good. And 1 minus e power minus alpha W is your design parameter. So, for a given material, you know what is alpha. What does alpha depend on? You can basically say that alpha, if you are tracking as a function of h nu, what is the alpha for h nu less than Eg? 0, there is no absorption, light will just go straight through, right, there is no absorption happening. But beyond Eg, you start having absorption, and you know, your alpha increases, and the rate at which it increases is primarily driven by the density of states, right. As you go to higher values of h nu, you are accessing deeper regions of your valence band and your conduction band, and in those deeper regions you have higher density of states, right. So, that will pretty much determine what your alpha is. So, alpha, which is typically expressed in terms of inverse centimeter. So, that actually, you know, gives us some thought. What it tells you is that this profile that I have drawn over here, the profile of how at the rate at which the power is absorbed within the material, that is actually for a particular wavelength or particular frequency. If the incident frequency changes, right. So, incident frequency changes, the frequency is much higher than the frequency for which I have drawn this red line. So, let us say the red line is at frequency mu 1, let us say corresponding to wavelength lambda 1. Then if you have lambda 2, which is much smaller, or corresponding frequency is much higher and the energy is much higher. If you have that, then all your absorption is going to happen over here. So, this is for lambda 2, where lambda 2 is smaller than lambda 1 or much smaller than lambda 1. Do you understand this? So, if you are going to a much shorter wavelength, which corresponds to much higher frequency and higher energy, then you have very high value of alpha, because your density of states is very high in those corresponding regions, right. And so, it will get absorbed within a very thin layer at the near the facet itself, okay. And that will, if it all gets absorbed over there, it's only under the influence of diffusion, and not all of that, I mean, not most of that current, most of those charges will get lost. I mean, they will just recombine among themselves, and they will lose that energy. So, it won't make it to the external circuit. So, you will have good responsivity for certain wavelengths. So, there are three domains that we are talking about. One domain is if you have a wavelength which corresponds to the band gap energy, right, that is where you start absorbing. Any wavelength which is greater than which has a corresponding energy which is less than the band gap energy is not going to get absorbed. Let me just draw that. I know there is a question back there, but I will just come back to that in a minute. So, this is responsivity as a function of wavelength, okay. So, let us say your eta line is like this. So, it's going to be, that's going to be guiding your responsivity. So, in terms of the responsivity, what we will find is there is a cutoff wavelength, right, corresponding to the band gap energy. Any wavelength greater than that cutoff wavelength is not going to get absorbed, because the energy is lesser than the band gap energy. So, there is no responsivity beyond this, zero responsivity beyond this. But within this, it's going to go, it's going to increase, and then it's going to be guided by your value of eta and then it's going to drop off, right? It's going to drop off abruptly because of the fact that at this point it's limited by ultra short penetration, because as you go smaller and smaller in wavelength, that corresponds to higher and higher energy, and it is such that all your absorption happens at the near the facet itself. So it doesn't generate a photocurrent in the external circuit. Okay, so then that will be the limitation. That's a question, but yeah. Sorry, 1 minus e power minus alpha w, yes. So yeah, that gets transmitted. So you typically have a contact layer that is fairly thin, but it also absorbs that light. It's a metallic layer, so it absorbs that light, and there could be a residual light that's coming out of that structure as well. Part of it could be, right? So part of it could be, yeah, we're just looking at the first level thing, but if you leave light over there, some of those photons can come back. But you typically design your photodiode for that longest wavelength of operation. So at the longest wavelength, it should be absorbed completely. So then you basically try to maximize that term. So you try to maximize that to 1. So e power minus alpha w, that fraction is going to be very close to 0. Yeah, that's one more question. Photodiode has a broad range of wavelengths that it's responsive. So yeah, so this thing typically for some, let's look at the case of indium gallium arsenide. So this is at 1.7 microns, and this happens around 0.8 microns. So it's actually fairly broad. Okay, so that is for indium gallium arsenide. And if you draw the same graph for silicon, with silicon, since it's indirect band gap semiconductor, it's harder to achieve a very high value of eta. So eta is somewhere around 0.5 typically, and the corresponding the band edge corresponds to 1.1 micron. So anything greater than 1.1 micron wavelength will go straight through the silicon, right? So it won't absorb any of that light, and within that it's going to go like this, and then it's going to fall off, typically about 0.4 microns. Now you have something called UV enhanced silicon photodiodes in the market, and they extend the absorption to even like 0.2 microns. And what they exactly do is you would have a much smaller structure to start with, right? It's a much thinner structure to start with. W will be very small. So it allows you to even for the shortest wavelengths, it still allows you to extract the photocurrent if you make it very short. Okay, so this is for silicon. You understand this picture? Yes. So very high penetration depth is, let's say, the width or the depth over which the power drops by 1 over E, right? That is typically the definition for the penetration depth, and that depth will be very, very short if you have very high value of alpha, right? That's what we are saying. Okay, so then the question is, that's my responsivity, and you know, it could be, the values could be in the order of 1 amp per watt. In silicon, it's typically about 0.5 amp per watt, right? The question is, can I get more photocurrent for the same power that's incident on the photodiode? How can I get that? How can I improve my responsivity? Okay. So let's look at that. How to improve responsivity. Okay. So that is actually done by a very clever manipulation of these layers. So you typically have a P and a N layer, right? Now what if you have another thin layer of P right next to the N layer, right? So what happens if you have something like this? Now in terms of the fixed charges, we can say that these are going to leave behind negative charges here, and positive charges over here, right? And so the corresponding charge density, you can say, is going to be like this, and over here it's like this, and then like that, right? Because there are some negative charges and then immediately some positive charges. So now if you look at the electric field across this structure, so this is basically the charge density rho, but if you are looking at the electric field across the structure, magnitude of the electric field, that's going to go like this, and in this region it's suddenly going to spike up because you have negative charge particles there, negative charged, negative fixed charges there on the P side, and then as you go, it's the field is constant, and then there are some more negative charges. So the field increases over there, and then the positive charges sort of neutralize this entire thing. So the field comes down. So you have a very high electric field that's within a very small region, or we have a very large voltage drop within a very small region. So what is the effect of that? You can say that when you look at the band gap around this particular point, by going to a very large voltage, what we are essentially doing is we are increasing the slope at which slope at that junction, the slope over which the energy drops down, right? So when that slope increases with external bias, you are essentially having a larger acceleration provided to the charges in that region. So specifically in this region, you are under influence of very high drift velocities, almost to the level of the saturation drift velocity, 10 power 5 meters per second. Under those conditions, you have a process that's called impact ionization. Basically, these charges have so much momentum, they are traveling at so high velocity that there is so much momentum that if they if they collide with any other nearby atom, they are going to just hit it and they are going to ionize that atom. So they are going to immediately have an electron pop off from that location, and you generate an electron hole pair. and those electron hole pairs still carry a lot of this momentum. So, those can go and create an impact ionization on the neighboring atom and so on. So, this entire process can multiply. And if you look at the impact ionization as a function of the electric field, we are tracking electric fields in the order of 10 power 5 volt per centimeter, very close to the breakdown strength of the material. Okay. 0, 1, 2, 3, 4, 5, and this impact ionization coefficient is an inverse centimeter, and that is 1, 10, 100, 1000 and so on. If you look at the impact ionization coefficient for indium gallium arsenide, for the electrons it will be something like this, and for the holes it will be something like this, right. With so holes have a smaller impact ionization coefficient, typically because the mobility of the holes is actually slower compared to the electrons in materials like indium gallium arsenide. So, this is for indium gallium arsenide, whereas for silicon it is like this. So, this is once again electrons and this is holes, and that's the thing you have for silicon. So, what it essentially says is that the impact ionization process in silicon happens at a much higher electric field or higher voltage, applied voltage compared to what you have for indium gallium arsenide. But one thing that matters is actually the width between the impact ionization for electrons with respect to the holes. So, in silicon that width is larger, meaning electrons you can get impact ionization happening at a much smaller voltage compared to when the holes actually go through impact ionization. We'll come back to that. We'll come back and see the difference between these two. But nevertheless, what we have now, because of this process of impact ionization, which happens beyond this threshold here, is your effective responsivity of this structure, which is called avalanche photodiode, right. That avalanche photodiode is going to have m times the responsivity of a PIN photodiode. So, that the process of impact ionization creates an avalanche of carriers, and so that is why it is called avalanche photodiode. And if you plot m as a function of that external bias, now you still are giving an external bias like this, Vb. If you plot m as a function of Vb, m equal to 1 over here, and it sort of increases exponentially as you go to higher Vb, and it will be limited by your breakdown voltage. So, beyond a certain voltage, that junction itself will punch through and it will break down, and then you won't be able to use that device anymore. But until almost until then you can get gain, right, and gains of 10 or 100 are possible through this process, and this is what you are going to try to do this week. You will actually look at PIN photodiodes and APD photodiodes. You will look at the characteristics of those photodiodes, and so you will try to quantify those. Okay. So, we are out of time, let us stop at this point, and we will continue. The other part of this is the response time, which I can tell you in general depends on the time it takes for carriers to go across the structure, right. So, the response time is going to be limited by the width of that structure. So, higher the width, lesser will be the response time, right. So, in that case the response time and the responsivity, there is a trade off. To get higher responsivity, you want larger width, so you can absorb all your radiation, but then your response time decreases. Okay. So, let me stop at this point, we will continue later, next lecture.